Hello again, everybody. I don't really have a plan for today's video. The last thing the class has covered has been Riemann sums, but I feel like those were explained pretty well. So I'm gonna just talk about kind of the relationships in calculus and physics on integrals, derivatives, and functions. So first of all, if we go to what is an integral, it's the area under a curve. So you get that by, this is our x-axis, this is our y-axis. So we think of the y as height and like x is length, and we have some sort of curve. And that's why we learned Riemann sums, because we can divide this into little rectangles and try and take the area that way, and all the way down, of course, right? And some of them will be above the curve, some of them will be below the curve, and hopefully everything evens out. But an integral is if we imagine each of these rectangles to be infinitely small in width so that we can follow this curve perfectly. And with an integral, we get the entire function basically multiplied by the length. So every height multiplied by the length, and we get a perfect area of the inside of the curve. And it makes sense that an integral is considered an antiderivative, because a derivative is a slope equivalent, right? We think of slope of a tangent line. And if we did the derivative of the entire function, it's the slope at every value of x. And our definition of slope, of course, is delta y divided by delta x. So where an integral is y times x, a derivative is y divided by x in its purest abstract form, right? And then, of course, the function itself is going to just be y. So in physics, the best way, I think, to look at this, the most common example, is position, velocity, and acceleration. So if I pick my middle function to be velocity, that's going to be meters per second, right? And in physics, the x-axis is normally time. So time in seconds. I'll do this. So v, meters per second, t, second. So if I have some velocity function, this graph is representative of the velocity as it changes in time. If I found the slope of this function, and of course we can estimate it, right? Slope of this function, this is going to be 0, and that's going to be a 0 point, I'll say right there. Increasing, well, positive but decreasing slope, we estimate it, and this is going to become maximum negative slope, and then back up. And of course these are just estimations, and you learn this when you're about to graph things. So I'm going to call this my v prime, or a slope. And that's just showing you for an example. And that's a graph of the slope of velocity. And if we go back to here, y divided by x equals slope. Therefore, v divided by time, which equals meters per second divided by seconds, so meters per second squared, equals acceleration. That's how that works, right? Basic position, physics, how you get there. Now also, if you do integral, we're taking the area under the curve, v times t equals meters per second times second equals meters. you get position, which again, sensible. That's where you get it. You don't have your starting value, and that's why in the previous video, when we were solving for antiderivatives, you always have that constant, because I don't know where it's going to start. All I know is that the speed right there was something. So I know what's going to be the change in position, and I have to be given an initial at some point to find out the full equation. But all of this math is the basis for it. And this is, I think, the simplest way to understand it. Another side note, I guess, is since I drew the derivative of the other function, I'll go through on how they're related, right? What we want to look for. So this is something that was taught to me by my high school teacher, I do believe. And no one else has really put it in this format. I really like this format. So I'm going to pretend that our position function, or f of x, I'm going to write out two basic functions here. So if I have x squared or negative x squared, and you'll see why we'll do this here. And I'll just make it x-axis. And of course, parabola at the middle. And over here, same thing. And this, of course, is a little bit more basic than at this point in calculus, but I feel like this is a really good basis to have. So we're going to do down parabola. Now, if I take the derivatives of these, we get velocity, or f prime of x. And the function turns into a line. So here I'll write out it's 2x here. We get negative 2x here. And I'll go back and show you why it matches so nicely. And I'm not worrying about the slope because this is just an estimation. I'm not putting any axes on. You don't need to worry about it too much. I need an exact value of the slope, right? Direction of the slope definitely still matters. I'll put some arrows to make it look less like just a bunch of lines. Last one, we have acceleration, or f double prime of x. And this will just be 2. This will just be negative 2. And what does that mean? We just have a negative function over here and a positive function over there. The reason why this is so nice is because now if I have a more complicated function, I can match each of these pictures to each other. So if I needed to find a visual derivative of something that looked like this, I know I've got a max here and a min there. So those go on the x-axis for our, so this is f of x, right? And we're finding the derivative. And so to there, this is an increasing function. It matches this type of curve. It's pointed down, but increasing. So I know the slope is going to be positive. The first derivative is going to be positive, but the second derivative is going to be negative because it's a positive slope, but it's getting smaller, getting closer to 0. So I know I draw a line like so. This bit, we have a change in concavity now because we have this bit that then runs into this one. So I know that it's going to go along this line and then turn into that line. So our slope, our derivative, is going to have some maximum value, and that'll line up with the change in concavity. Right. Now following along with how it goes, we go back up, positive line again, 0. I can just tip that out. And it's just visual, so we don't need to worry about any particulars. If I wanted to do, so an antiderivative of this would be a little bit more curvy, right? Because these mins and maxes are going to be, these mins and maxes are going to be inflection points of this guy's antiderivative. And since it doesn't cross the x-axis anywhere, it's not gonna, this function's not gonna have any mins and maxes. That's where we start with. I won't go too far into it, because mainly I just want you to see the relationship between them. And this to me is like the core of calculus. Once you get this and you can see them in your head, it's a lot easier to solve them algebraically. And the most practice I think you have is solving them algebraically, but it's nice to think of them in your mind. If you have any questions on Riemann sums or what you're currently on, please comment or leave anything else. But I feel like this is a good video, a good topic for you to know in your general understanding of calculus. Yeah, thanks, and hope you have a good weekend.